Welcome to my channel, all of you. Today's session will be on quantum numbers. The four set of quantum numbers, what are their significance? What is the difference between orbit and orbitals? What are the shapes of orbitals and so on? So let us start our discussion without much delay. Hello all of you. Today's topic is quantum mechanical model of atom. Here, the motion of the macroscopic objects were previously described in terms of classical mechanics, and we know that classical mechanics is based on Newton's laws of motion, and basically they were talking about particle nature. Okay, so they have predominantly particle like nature. We were talking about macroscopic objects where classical mechanics explain them. But microscopic objects cannot be explained, the properties cannot be explained by classical mechanics. Rather, the dual behavior, the dual nature is coming into play where both the observable particle-like and wave-like properties are accepted. Quantum mechanics is a theoretical science that takes into account the dual nature of matter. That means quantum mechanics accepts the dual nature of matter, emphasizes the dual nature of matter, and puts forward the basic structure or rather model of atom on the basis of quantum mechanical postulates. It was independent, that means it was developed independently in 1926. Quantum mechanics was developed independently in the year 1926 by Werner Heisenberg and Erwin Schrödinger. Now, Heisenberg we have seen in the Heisenberg's uncertainty principle. We know about Heisenberg. Schrödinger is the new name, the new scientist we have to know. Based on quantum mechanics, a new model of atom was developed and which was known as the quantum mechanical model, and the work was during the 1920s. And what happened in this model? The behavior of an electron in an atom was described by an equation by Schrödinger and which was known as Schrödinger's wave equation. This is the Schrödinger's wave equation, the complete equation, where we can see that the first three, del 2 psi del x2, del 2 psi del y2 double derivative, del 2 psi del z2. These are the position coordinates. Why? Because these are the space coordinates. These talk about the position of the electron in space. And rest part of the equation, that is the entire equation plus 8 pi square m by 8 square E minus V psi equal to 0. That means the second part of the equation talks about the energy factors. E is the total energy, V is the potential energy of the electron. So the first part of the equation deals with the position of the electron. The second part of the equation deals with energy parameters, energy factors. Now, here you have seen the function psi, the mathematical operator psi. Here you have seen everywhere the mathematical operator, you have seen psi. Now, actually here what it is? Psi is the function, and it's the amplitude of the electron wave called the wave function. So psi is the wave function. Keep in mind that all the information about the electron is present in this psi. Okay, all the information regarding the electron is present in the psi, and mathematically you can say it is the amplitude of the electron wave. Okay. Now the simplified version of this equation is H cap, we can see. That is the mathematical operator. H psi is equal to E psi. And this mathematical operator is known as Hamiltonian operator. And when there is an equation, there is a solution of the equation. So here, the solution of the Schrodinger wave equation is known as the wave function, which you have seen as psi. So psi is the wave function. It is the amplitude also of the electron wave. And it is the solution of the Schrodinger equation. That is the reason I was telling it is the function. Just see. Because when you solve this equation, you will get many values of psi. But all the values are not permitted values. Okay. All the values are not permitted values. There are only certain permitted values, certain permitted solutions of, and these are the wave functions, and they are known as eigenfunction. That means the permitted values of psi, the wave function, is known as the eigenfunction, and these permitted values correspond to definite energy state and is called orbital. So the concept of orbital actually is coming from the quantum mechanical standpoint, from Schrodinger's wave equation. Now each energy state or the orbital, it is characterized by a set of 3 quantum numbers. And what are those 3 quantum numbers? N, which is known as principal quantum number, L, which is known as azimuthal quantum number, and ML, which is known as magnetic quantum number. We are going to deal with them now one by one. Principal quantum number N, small n, is also the shell number. And it is the K shell, L shell, M shell, N shell. These all we have seen. We know the shell number is principal quantum number. And from the positive nucleus, when we go out, when we go outwards, then the value of N gradually increases. So N is equal to 1 is closer, N is equal to 2 is away, N is equal to 3 is even more away, like that. That means with the increase in the value of N, the distance from the nucleus goes on increasing. The second quantum number, which I said azimuthal quantum number, that is given by L, and the concept is it gives the subshell, or it is also known as orbital angular momentum quantum number. Why this quantum number is related to the orbital angular momentum, we will just discuss few minutes later. Let us see what this azimuthal quantum number is. It determines the angular momentum of the electron. It also determines the shape of the orbital in which the electron is located. And it can have values 0 to n minus 1. L can have values 0 to n minus 1. So for that I have shown you here one table where we are seeing how it is related to 0 to n minus 1 just now I said. So when n is equal to 1, that is the K shell, L can have, just now I said 0 to n minus 1. So it's only 0. And that is the S subshell. And this S subshell corresponds to n is equal to 1. And so I have written 1s. Now for the next principal quantum number, n is equal to 2, L shell can have these two values 0 and 1, and 0 and 1 corresponds to S and P, which is corresponding to n is equal to 2, so we will say 2S and 2P. N is equal to 3. The shell number is 3 and the shell is M shell. It can have values, L can have values 0, 1, 2. It can have values 0, 1, 2. So 0 is S, 1 is P and 2 is D. So we'll say 3S, 3P, 3D. Next, N is equal to 4. That means the capital N shell. It can have values 0, 1, 2, 3. That is S, P, D, F. And they correspond to N is equal to 4. So it is 4S, 4P, 4D, 4F. And so on. It goes on like this. For N is equal to 5. It goes on like this. So the next quantum number is the magnetic quantum number, which is denoted by ml. The magnetic quantum number denotes the different orientations of the electron cloud in a particular subshell. So actually it talks about orientations in space, how the orbitals are oriented in space. So it gives the shape of the orbital, of course. The final shape of the orbital is given. So the number of orbitals in a particular subshell is given by plus L to minus L including 0 for a particular principal energy level or for a particular shell number that I have shown you here. Let us see. Okay. Now let us see over here N shell. N shell, that means N is equal to 1, K shell, N is equal to 2, L shell. That means the value of N is giving the shell. The value of L is giving the subshell. The value of ML is giving the orbital, and they are highlighted. We can see. Number of orbitals is denoted by 2L plus 1. So how ML we are getting? ML I said we are getting from plus L to minus L including 0. Plus L to minus L including 0. So N is equal to 1 has L equal to 0. S subshell. And it is having only one orbital like this. Okay. So this is 1s. Next, N is equal to 2. That means L shell. L shell is having two subshells because small l, azimuthal quantum number, can have values 0 to n minus 1. That means 0 and 1. So S and P. Now ML can have, for S the value is 1, only one orbital. But for P the orbitals are 3. Because for P, L has a value of 1 and plus 1, 0, minus 1. These are the three set of degenerate orbitals. Degenerate orbitals. What is the meaning of the term degenerate? The degenerate term means of same energy. They are all having same energy. And how many? Plus 1, 0, minus 1. That means 3. Put to the formula 2L plus 1. So L is equal to 1 for P subshell. So 2 plus 1, 3. That corresponds to Px, Py and Pz. Next, moving on to M shell. M shell has N is equal to 3. L can have values 0 to n minus 1. So 0, 1, 2. And it is having S, P, D corresponding to 3 shell numbers. So 3S, 3P, 3D. Now let us see the orientations, the shapes, the orientations. For S, the ML value is 1. For P, L has a value of 1. So there are 3 set of degenerate orbital. For D, L has a value of 2. So we have plus 2, plus 1, 0, minus 1, minus 2. We have 5 set of degenerate orbitals. And these are the 5 set of degenerate orbitals we can see. dxy, dyz, dzx, dx square minus y square, dz square. Put into the formula 2L plus 1. L is equal to 2. 2 2s are 4 plus 1 is equal to 5. So like this, you have to understand the concepts. After this, in a different manner, I have shown the spin quantum number. There is a reason why it is shown in a different manner, because it does not follow from the wave mechanical treatment, but it's an evidence, or it's an outcome of the spectral evidence of electron in motion, where we can see, like our solar system, that what happens, all the planets revolve around the sun, the planets are revolving around the sun, and the planets are also rotating around its own axis. Similarly, we'll say that The electrons are revolving around the nucleus and rotates or spins about its own axis. Rotates or spins about its own axis. So it determines the orientation of the spin angular momentum. The spin angular momentum is quantized and can have two orientations. What are those two orientations? The spin can be in a clockwise manner or in an anti-clockwise manner, and the values that are given for it is plus half and minus half, spin up और spin down. ऐसा कोई मतलब नहीं है कि ये इलेक्ट्रॉन spin up होगा दूसरा spin down होगा. It can be any electron getting a plus half, the other one will be minus half. Okay, so due to the spin, the electron behaves. See, electrons are negatively charged and they are having the spin property for which they behave as tiny magnets, and for that reason they give magnetic property to the atoms, molecules or ions. Now, if all the electrons in an atom or molecule are paired, then the substance is diamagnetic. What is the meaning of the term diamagnetic? They are weakly repelled by the magnetic field. When it is happening, when all the electrons in the atom, molecule or ion you're talking about, the substance you're talking about is paired. If one or more unpaired or odd electron is present, that means presence of at least one unpaired electron can make the substance paramagnetic. And what is the meaning of this term paramagnetic? How is the magnetic behavior? It is weakly attracted by the magnetic field. I hope this part, spin angular momentum, is clear. If not, then please rewind, go back and listen to it once more. Okay, moving on to the next concept. See, I said there is a relation between the orbital angular momentum and the azimuthal quantum number. This is the mathematical relation. Okay, the orbital angular momentum is equal to root over of L into L plus 1 into h by 2 pi. Now this h by 2 pi is given as h cross. Okay, so this is the expression. Next, calculation of the magnetic moment mu of a substance. Magnetic moment, if I have to talk about the magnetic property of the electron in spin, having the spin and having the charge, then we can be told to calculate the magnetic moment. Now Bm stands for Bohr magneton, that's the unit. And how to find it? Root over of n into n plus 2, where n is the number of unpaired electrons. Now, Schrodinger's wave equation cannot be solved exactly for multi-electron atoms. So I can say that it is applicable for hydrogen and hydrogen-like atoms. I mean species. Why? For a single electron species. Now, the main postulates of the quantum mechanical model of atom hence can be given as, from all the discussions, it can be given as energy of electron in an atom is quantized. That means when I'm talking about n is equal to 1, it has a fixed energy, say E1. When I'm talking about n is equal to 2, it has a fixed energy, say E2. That means the energy is quantized, is fixed. The exact position and velocity of an electron cannot be determined simultaneously, and that is what was told by your Heisenberg in its uncertainty principle, right? So we consider the probability of finding the electron in different positions in an atom. So now can you understand why this quantum mechanical model is related to individual works of Heisenberg and Schrodinger? Now, next, about psi, what is said in the Schrodinger's wave equation? Psi for an electron in an atom, it represents the atomic orbital. Now, you should understand one thing, that the atoms have atomic orbitals. The atomic orbitals, when in molecule, form the molecular orbital. Now, the psi, the wave function, the solution of the Schrodinger wave equation actually depicts atomic orbitals and is associated with a definite amount of energy. An orbital cannot contain more than 2 electrons. This is very important, that I cannot fill electrons when I will be doing in the next session, filling of electrons in orbitals. We'll see that here again there are certain rules. So this was again said in the quantum mechanical model, the orbital cannot have more than 2 electrons. Next, all the information about the electron in an atom can be obtained from the orbital wave function psi. That is what I told when I was explaining the Schrodinger wave equation, that contained 2 parts. One is the position, the other is the energy factors. There I said psi is the solution, psi is the wave function, and all information about the electron is obtained by psi. Now, if I cannot locate an electron exactly along with its velocity, then what can we do? It says that there is a probability of finding an electron at a point within an atom. And the probability is proportional to square of the orbital wave function. So psi was the orbital wave function. Mod psi means the magnitude I am taking and square of it. As such, squaring it makes it positive. So mod psi square actually gives the probability of finding an electron at a point, and the square of it is known as probability density and is always positive. Okay, this is what we can visualize, we can see. This is the Bohr orbit, the circular orbits, Bohr orbit, electron rotating around it, around the nucleus. And orbital concept, if you can see it properly, you will see the shading is there. The shading shows the probability density concept, the region in space where the electron is most likely to be present. So here you see an orbital may be defined as the region of space around the nucleus where the probability of finding an electron is maximum 90 to 95%. So no one can say here only I can see an electron. No, this is the region where the probability of finding an electron is maximum. This can be said. This is the orbital concept and this is the quantum mechanical output. Now, here are the difference between orbit and orbital. See, orbit is well-defined circular path followed by revolving electrons around the nucleus. So what is important is it is well-defined circular path. But orbital is the region of space around the nucleus of the atom where the electron is most likely, see, most likely to be found. Now, orbit is a planar motion of an electron, this concept. Orbital is a 3D motion, 3D aspect of the electron. Now, orbit, the maximum number of electrons in an orbit is 2n square. That we'll see, where n stands for number of the orbit. That means if I say orbit n is equal to 1, it can have maximum number of electron as it can have 2. N is equal to 2. Then the maximum number of electron in it will be 2 into 2 square. Likewise, so it will be 8 like this. Okay. But an orbital can accommodate not more than 2 electrons, that we have said. Orbits are circular in shape and orbitals have different shape. That again we will see. See, S orbital is said to be spherically symmetrical. P orbital has a dumbbell. D orbital has a double dumbbell shape. These all are the outcomes of the radial probability distribution as well. Okay. Orbits are non-directional. They are non-directional in character. But orbitals, they have particular orientation. Like for P, I said Px, Py, Pz. That means Px is oriented towards x-axis, Py is oriented towards y-axis. So I'm talking about orientations, directional character. Now, orbit concept of well-defined orbit is against the Heisenberg's principle. That means I am able to locate the electron in this particular orbit. But the concept of orbital, where I am telling it is the region of space around the nucleus of an atom where the electron is most likely to be found. If I say this, that means I am talking about uncertainty. I am talking about possibility, probability. So this is in accordance with Heisenberg's uncertainty principle. So this is what I was talking about. These are the boundary surface diagrams, or these are known as contour surface diagrams. And the s orbital, this is your s orbital, spherically symmetrical. Remember that the s orbital is closest to the nucleus. It is closer, or closest if I say 1s. So closer to nucleus. Why? Because it actually surrounds the nucleus uniformly. The distribution, the electron cloud is uniform. Now for these are for 2px, 2py, 2pz, and we can see over here this is a dumbbell shape. This is a dumbbell shape. So this is a spherically symmetrical shape. This is said to be spherically symmetrical. Okay. And this is said to be dumbbell. See, px, 2px, it's oriented towards x-axis. 2py, oriented towards y-axis. Now the axis is towards z-axis for 2pz. And for d orbitals, this is known as double dumbbell shape. One dumbbell that we are seeing in P, two dumbbells in D. See, dxy is along the x and y plane. dyz is along the y and z plane. dxz is along x and z plane. Dx square minus y square, see here x and y, and the lobes are like this. These were previously the things were, they were in between the plane. See, these were in between the plane. Here again, in between the plane. But this is along the plane. This is along the, I want to say along the axis. Okay. So here this is in between the plane. But in case of dx square minus y square, it is along the axis. Now dz square. dz square, we can see a ring over here. It's like this. It's along the z axis. And then a ring like this. Okay. The symmetry of the lobes are, if one is having one type of symmetry, the other lobe is having opposite symmetry. So again, one I am highlighting, the other I am not highlighting, to show that if one is having one type of symmetry, the other is having a different symmetry. Okay. Next, going on to the nodal surfaces. Node. What is node? Node means we are talking about regions in space where the probability of finding an electron is maximum, and that is the orbital. Now in the orbital, there are some regions where we are not having the probability of finding an electron, and those spaces are known as nodal space, or the nodal surface, or the nodal point. So see here, the point at which the probability of finding the electron is 0. That is known as nodal point. And how do we know how many nodal points will be there? For that we have this. Number of angular nodes in an orbital, if it is L, then the number of radial nodes will be n minus L minus 1. So total number of nodes in an orbital will be n minus 1. So radial nodes will be n minus L minus 1. So here we are seeing for a 4p orbital, how many angular nodes are there? See, this is 1 point. How many angular nodes are there? L. So for L is here we are having only 1. Now number of, why 1? L is equal to 1? Because it's P. For P subshell, L is always equal to 1. So that we have seen. Now number of radial nodes is said to be here n minus L minus 1. So n is equal to 4. L is equal to 1. So 4 minus 1 minus 1, 2. Here, third thing, total number of nodes in an orbital. How many total nodes are there? N minus 1. So 4 minus 1, 3. 3 total nodes will be there. Of course, 3 total nodes corresponding to px, py, pz. Here I am not finding any probability of finding an electron. Here there is the lobe shows a probability. So there are likewise px, py, pz. There are 3. So obviously there will be total number of 3 nodes. Now, the number of atomic orbitals in nth energy level. How many total atomic orbitals will be there in the nth energy level? There we'll see it is for n is equal to 1, number of atomic orbital will be n square, no? So it will be 1 and it's 1s. For n is equal to 2, n is equal to 1 means K shell. For L shell, n is equal to 2 and it can have 2 square. So 4. 4, how do we know? See, for n is equal to 2, for n is equal to 2, L can have values 0, 1 and it's 0 and 1 only because it is 0 to n minus 1. Okay, so 0 stands for S and 1 stands for P. So for n is equal to 2, it is 2s and 2p, and 2p means ml can have values plus 1, 0 and minus 1. So it is 2px, 2py, 2pz along with 2s. So how many we saw? 1, 2, 3 and 4. So by the formula n square also we are getting to know we will have number of atomic orbitals maximum 4 for n is equal to 2. Now for L and for M shell it will be 9. Why? 3 square 9. Let us just check it. N is equal to 3 can have L values 0, 1, 2 and ML can have values for L 0. For 1 it can have plus 1, 0, minus 1. For 2 it can have how many? For 2 it can have plus 2, plus 1, 0 and minus 1 and minus 2. So here it's 1, 2, 3, 4, 5, 6, 7, 8 and 9. That's why 3s, 3s, 3px, 3py, 3pz, 3dxy, 3dyz, 3dzx, 3d x square minus y square and 3dz square. So that's all for this session. We will be meeting in the next session where we will be talking about filling of electrons in orbitals, what are the rules, how to do it and all. So bye all of you. Thank you all of you for being with me and for being partners for this session. Happy learning to all.